Hey everyone, welcome to another episode of Science Saturdays with Noah. I'm your host, Noah Mugen. I've loved science for as long as I can remember, and I hope that through these videos I can share that love of science with all of you. This week we'll be tackling the science of insulation, which relates back to last week's video on heat loss and entropy. If you haven't seen that one, I would recommend that you go watch it, but it won't be necessary for today's activities. Now, speaking of activities, I'm going to quickly go over the materials that you're going to need for today's experiments. Don't worry if you don't have all of them, it's easy to follow along with the video. Today we're going to be using 2 cups, preferably microwavable, either hot water or hot chocolate, some aluminum foil, a sock, a thermometer, some bubble wrap, and then some plastic wrap, vegetable shortening for cooking, 2 ziplock baggies, a bowl, and some ice water. Now winter's finally approaching and the weather's getting a lot colder. I finally have an excuse to wear this. But that begs the question, why does this help against the cold? Last week we learned about entropy and how heat will always move from warm to cold objects, bringing them closer in temperature. But why does this sweater slow that transfer of heat? Well, to understand that, first we're going to need to understand the 3 ways that heat can be transferred: conduction, convection, and radiation. Conduction is the transfer of heat from a usually solid substance. In conduction, the heat energy moves between the specific particles of the substance passing through it. Conduction is happening right now. I'm sitting on this ground, and heat energy is moving from my body through my shoes into the pavement. Convection is the transfer of heat energy through a fluid. A fluid is something that's like a liquid or a gas that will flow, basically. In convection, the heated substance itself moves around and flows around me, so that the hot part moves away and the cold part can come near me to get heat energy. Or it can be in reverse. If I'm colder than it, the hot part will come to me and transfer heat energy as it's flowing around. Convection is also happening right now in the air around me. I'm heating it up and it's flowing around so that I'm always heating the cold air. The third way heat can transfer is radiation. Radiation is the transfer heat between 2 objects or substances that aren't actually touching. In radiation, heat is transferred through a form of energy called electromagnetic waves. These are like radio waves or light. It's basically how heat is transmitted like a wave through space. One example of that is right now the sun. The sun is radiating heat from itself onto me, warming me up, along with everything else around me.
Now there are 4 factors that affect the speed of heat transfer between substances. The first factor is going to be conductivity. Conductivity is basically how well heat or other energies can move through the substance, basically how quick the heat can travel through the substance into something else. The second factor is going to be the temperature gradient between the 2 substances. Now the temperature gradient is really just the difference in the heat energies that the 2 have. The larger the temperature gradient is, the faster heat is going to want to equal itself out. The third factor that affects heat transfer is the thickness of the substances. The thicker or wider a substance is, the slower that heat energy is going to be transferred through it because it has just, more area, more distance across. Then the fourth factor that affects the rate of heat transfer is the surface area of the substance. The larger a surface area a substance has, the faster heat will be able to get through it because there's more places for the heat to escape or to enter. And yes, different substances are able to transfer heat better than others. We're going to show that right now. For this experiment, you're going to want to grab 2 cups and fill them with some sort of hot liquid. You can just use warm water, or if you're feeling festive like me, you can use hot chocolate. Then you're going to grab a sock, some aluminum foil, and a thermometer. Make sure that these cups have warm liquid inside them and that they're about at the same temperature. Now, around 1 cup, you're going to place a sock. Make sure not to spill it, be careful, and ask an adult if you need help. There we go. And in the second cup, you're gonna wrap it with the aluminum foil. Make sure that the tops of these cups and the bottoms are covered by their respective surroundings. All right, so now you have one cup filled with warm liquid and covered by aluminum foil. And you have another cup filled with warm liquid covered by a sock. The liquid inside the cup is the same in both cups. But now feel the cups. Which one feels warmer? It should be that the one surrounded by the foil feels a lot warmer than the one surrounded by the sock. How can that be? The liquid inside is the same temperature. Could more heat be traveling from inside this cup into your hand than from the sock covered one? How is that going to affect the loss of heat? Well, let's see. You're going to grab these two cups and carefully, making sure not to spill what's inside of them, place them in the refrigerator. After about 5 minutes, you're going to take the cups back out of the refrigerator. Bring them back here. Now carefully, you're going to unveil them. Take the coverings off. Remember, this was the hot chocolate covered by the foil, and this one was the one covered by the sock. Now you're going to take your thermometer and measure the temperature from the one that was previously covered by the foil. Remember, these started out as the same temperature, but what we're about to see is a difference in temperature between the two of them based on their coverings. Which one do you think is going to be hotter? Which one do you think is going to be colder? Why do you think that? This one is at 39 degrees Celsius, or about 102 degrees Fahrenheit. Shake it off, you don't want to get hot chocolate on your table. Now we're going to measure this one. Ooh, that's a big difference. This one sits at around 43 degrees Celsius, or 110 degrees Fahrenheit. So the one covered by the sock was actually hotter than the one covered by the foil. But how could that be? When we felt the foil one at the beginning, it felt hotter. So why all of a sudden is this one actually hotter? Well, it's because the foil was actually letting heat energy out faster than the sock did. We could feel that because as the heat energy was being let out faster than this one, it was interacting with our hands and making it feel warm. At the same time, though, that meant that heat energy was leaving the foil-covered one. So even though it felt hotter, it was cooling down much faster than this one, in which the sock was actually keeping all that heat energy inside of it. And these differences were a result in the differences between the two materials surrounding the cups. Specifically, the sock is an insulator while the foil is a conductor. Insulators, like cloth, are really good at keeping energy where it is, keeping that heat energy contained. They keep cold things cold, and they keep hot things hot. That's why when we felt the cup at the beginning, it didn't feel that hot because the cloth was preventing this flow of energy outside of it. And then when it was in the fridge, the cup stayed hot because, again, the cloth kept that heat energy from leaving the cup. On the contrary, foil is a conductor. Conductors are really good at letting heat energy transfer happen. Any sort of energy transfer or heating up works really well with conductors. Have you ever touched a hot car seatbelt in the summer and you burn your hand? That's because that's a really good conductor. And all that heat energy is able to really quickly move into your hand. The conductor in the cup, surrounded by the foil, allowed the heat energy to quickly leave the cup, both heating up our hand and also losing that energy into the refrigerator. There are several ways that insulators can work. Some, like the fabric of our clothes or the fur of animals, take advantage of the different types of heat transfer. Remember, heat can move in three ways: convection, conduction, and radiation. In our clothes and animal fur, they're composed of tiny little things, either fibers in the clothes or hairs in the animal fur. These fibers or hairs create tiny little air pockets within the insulating covering. These air pockets slow the conduction of heat energy, since that can't happen through air. As such, it really puts a damper on how heat can move from the inside to the outside of the material, or vice versa. That's how our sweaters and animal fur is able to keep us warm in the wintertime. And we can show how these air pockets affect the transfer of energy with a simple experiment right now, which is really similar to the one that we just did. Again, you're gonna grab 2 cups full of some sort of hot liquid. Right here I have hot chocolate, but you can use just warmer hot water if you want. Around 1 cup, you're gonna place some bubble wrap. Make sure to cover both the top and bottom of it, as well as the sides, of course. Remember, be very careful to not spill any. Not because that would disrupt the experiment that much, just because, you know, your mom might get mad at you by making a big mess on the kitchen table. Now, you're gonna get the other cup and wrap it in some plastic wrap. Now, surrounding these cups, there is the same amount of plastic. The only difference is that the bubble wrap has a lot of tiny air pockets within it. Now, like before, you're gonna feel the 2 cups. Which one feels hotter? The one surrounded by just the plain plastic wrap should feel a lot hotter than this one. Now, based on what we learned last time, what do you think this will say about what will happen when we place these 2 in the fridge? Which one is going to lose its energy the fastest? Well, let's find out. Take both your cups, full of the hot liquid and surrounded by their respective materials. You're going to go place them in the fridge.
A new year brimming with happiness is the heartfelt wish of these hometown merchants. Extend all the wonderful people of this community.
And again, after 5 minutes, you're going to take these cups back out of the fridge. Set them back here. Carefully take off their coverings. Set them down. Take your thermometer, place it in this one. This one was covered by the plastic wrap, remember? And this one was covered by the bubble wrap. All right, this one reads about 46 degrees Celsius, or 114 degrees Fahrenheit. Now place it in this one. Ooh, it's getting hotter. This one goes about as far as my thermometer will go, but right now it reads 50 degrees Celsius and 120 degrees Fahrenheit. It's probably hotter than that, but that's all that this one's going to show. But that's all it needs to show, because it shows that this one is still a good bit hotter than this one. The plastic wrap was able to preserve the heat energy in this better than just the plain regular. I'm sorry, the bubble wrap was able to preserve the heat energy and stop heat transfer better than the plastic wrap was, because the air bubbles within this were able to slow down the conduction of heat energy. This one acts as a far better insulator, and thus the heat energy and the warmth was kept inside the cup. Again, that's why this one felt hotter in the beginning, yet it cooled down faster. The heat energy was able to move through the plastic wrap much better, and so it moved into our hands and allowed us to feel it, but it also moved out into the refrigerator air. Now there's another way that insulation can work without taking advantage of air pockets. Lots of animals that live in the Arctic, like bears, whales, walruses, have a big layer of fat surrounding their body called blubber. This blubber is very thick and very dense, meaning that it's hard for heat to transfer through it and takes a long time. As such, this blubber acts as a really good insulator, as most of the heat is kept within the animal, protecting it from the cold Arctic waters. And for our final experiment, we're going to be replicating those effects of blubber. For this one, you're going to grab a large bowl and fill it with ice water. You're also going to grab a container or bag of shortening and 2 small sandwich baggies. First off, place your hand inside one of the sandwich baggies, pull back your sleeves if you're wearing long sleeves, and stick it into the ice water. That ice water is cold. Imagine this is the water of the Arctic. All that cold water is taking the warmth from your hand. And if you're a creature in the Arctic, you couldn't stay in that water like that for very long. Now, grab your shortening. You're gonna open it up, place your hand inside of another ziplock baggie, and put it in the ice water. And put it in the shortening, I mean. This shortening is really thick and dense, and it's going to act as the blubber. Now, place that inside the ice water bowl. I don't even feel anything inside the thing, inside the shortening. I place my hand in there, and the ice water is surrounding the bottle of shortening, or container of shortening, and with it my hand. My hand doesn't feel cold at all. It feels like normal. This is how Arctic animals use their blubber to stave off the Arctic oceans. The blubber protects them and keeps their heat energy inside, preventing the transfer of heat into the cold water and letting them swim and catch fish and live as any normal animal would.
It's important to keep warm in the wintertime, and we can do that by wearing insulating clothing. Our clothes use air pockets to keep us warm, while other animals, like walruses or whales, use blubber to keep themselves warm and keep the heat energy inside themselves, stopping it from releasing into their cold environments. Well, that concludes another Science Saturday with Noah. I thought it was really fun, and I hope you had fun too. Thanks for tuning in, and I'll see you again soon.